Welcome to Signal Processing Laboratory. So in this video we are going to see about the realization of adaptive filter using LMS algorithm and solved using Steepest-Descent algorithm. So we have already seen about the adaptive filters. So it's just a type of filter where we can change the filter coefficient based on the time varying input signal. So in this experiment we are using the least mean square algorithm. So it's a part of the group of stochastic gradient algorithms. The update from the steepest descent is straightforward, while the dynamic estimates may have the large variance here. So the algorithm is recursive and effectively averages the estimate values. The simplicity and good performance of this LMS algorithm makes it benchmark against which other optimization algorithms are judged. So this algorithm is prevalent among most various adaptive algorithms because of its robustness. So it is based on the minimum mean square error criteria. So the LMS algorithm is based on the concept of steepest descent that updates the weight vector as given in this equation. So here the mu is the step size that determines the stability and convergence of the algorithm. The comprehensibility of the algorithm depends on the fact that it does not require any gradient to be known, implying that it is estimated at each iteration, unlike the steepest descent approach. So in an LMS algorithm, so there is no need the gradient to be known, so it is estimated in each iteration. So the steepest descent direction gives the greatest change in the elevation of the surface of cost function for a given step laterally. So the steepest descent procedure uses the knowledge of this direction to move to a lower point in the surface and to find the bottom of the surface in an iterative manner. So consider a system identification problem in which the output of a linear FIR filter must match to the desired response signal. So this is the response signal D of n. So the output of this FIR filter is given by this equation, that is D of n is equal to W T of n into X of n. So the D of n is the response signal, whereas the X of n is the vector of input signal samples, and W of n is a vector containing the coefficient or the weight of this FIR filter. Now the coefficient vector W of n needs to be found out that optimally replicates the input-output relationship of the unknown system such that the cost function of the estimate error. So we are going to find the, so next we are finding the cost function of the estimation error. So E of n is equal to D of n minus D of n. So it is the smallest among all possible choice of this coefficient vector. So an apt cost function is to be defined to formulate the steepest descent algorithm mathematically. So the mean square error cost function is given by J of n is equal to error function. So it's based on E of n square. So it is nothing but the error function, so that is D of n minus W into T of n X of n whole square. So where J of n is the non-negative function of the weight vector. So now let's execute the program for the adaptive LMS. So here we are calculating the coefficient vector and mean square error cost function. So as we seen in the theory section. So this is the desired signal, but it is corrupted with a noise. So the noise with the desired signal with noise added signal is displayed here. So then we are estimating the signal, that is the response signal. After that we are finding the error signal here. Similarly, this is the program using Steepest-Descent algorithm. So here also we are having a signal. So this is the desired signal corrupted with noise, and the estimated signal. So the output error signal. So we will see the next experiment in the next video. Thank you.